And we share the screen here. We have made some good progress already in terms of the coverage, and we filled up even the gaps. Last time we covered the topic of the safety ethics, and for the rest of the semester, suggesting that some of you may end up designing or operating new nuclear power plants, and innovation has to take shape at some point, then we would like to be cognizant of the different accidents that where things went wrong in the history of the nuclear industry. And that's the title of our class, as a matter of fact. And this is the only place where the ambition has been to cover all the known and unknown accidents and somehow compare them to each other. For instance, you'll find a great similarity between the wind scale accident that happened in the UK and the Chernobyl accident that unfortunately was not taken into account. So in that case, we would like to cover all the different accidents, having covered the phenomenology, say how a steam explosion happens, how a loss of coolant accident happened. In fact, these are description of actual accidents. Like when we covered the chapter on the loss of coolant accident, that was a description of the 3 Mile Island accident. It was a small loss of coolant accident in that case. And when we deal with the, let me see how I can get you in. Boy. You'll find a similarity also between the wind scale accident and the Chernobyl accident. And unfortunately, the prior accidents were not really considered when almost the replicas of the earlier accident have happened. So we would like to be able to learn about those accidents. Later on, we'll come back to the safety of gas-cooled reactors, of heavy water reactors, and so on. But I would like to cover the accidents. The way I'm going to cover it is not from the perspective of seriousness. Obviously, Fukushima has been the most serious of accidents. I'm going to cover it from the perspective of historical occurrence. And the first one accident that the nuclear industry had to deal with was the experimental breeder reactor number 1. And so this is the first description. Actually, that accident that happened in the experimental breeder reactor number 1 was intentional, because they generated the accident intentionally so that they can learn about how a fast reactor would operate. And historically, the interesting thing is that the experimental breeder reactor number 1 was the first reactor to operate in the United States. It was built in the desert around Idaho Falls. Our TA has been last summer at Idaho Falls. Idaho Falls is the Idaho National Engineering Laboratory. It is a lab in charge of the safety aspects of nuclear, not just operating power plants, but also naval reactors. So they run experiments in the desert there of Idaho. Right now, that EBR-1 reactor is a museum that you could visit on your way out west, maybe on a trip over the summer. Don't travel in that area during the winter. It's a very, very dangerous area in that case. It produced, thank you very much. It produced electrical power for the first time from nuclear energy on December 20th, 1951. And in 1953, it confirmed that a reactor that is built to operate in the fast neutron range is capable of breeding more fuel than its operation consumes. And this is the vision of nuclear energy. It's not being applied today because we are using only the new uranium-235 isotope from uranium. But for the long term, we could use the other isotope, uranium-238, converted into a fissile isotope by the process of breeding. And the fascinating aspect of nuclear energy there, or the vision of nuclear energy, is that you can produce more of the fissile isotope than what you consumed in making it through the process of breeding. Hence, you have an unlimited supply of energy if, say, one of two cycles are adopted, the uranium-238, uranium-235 fuel cycle, or even more interestingly, and that's a topic of current research in many countries like the Europeans, France, as well as China, is the use of the thorium fuel cycle. Thorium is an element that has only one single isotope in nature, thorium-232, being an even numbered isotope. It is not fissile. You cannot turn it into a critical mass unless you absorb a neutron from say, uranium-235 fission initially, and in that case, you produce thorium-233, decays into protactinium-233, and then into uranium-233. The interesting thing is that thorium is 4 times more abundant in the Earth's crust than thorium, and also it has another advantage, is that you cannot turn it into a weapon like uranium-233 because it comes mixed with the isotope uranium-232, which decays to thallium-208, and that is a very, very powerful gamma emitter. So you cannot build nuclear weapons from uranium-233 unless you simply separate it quickly and use it immediately after separation. So this type of reactor used, of course, and proved that we can breed from the uranium-235, uranium-238, plutonium-239 fuel cycle. Interesting enough, it used a liquid metal. Why a liquid metal? Because when you use a liquid metal, the moderation of the neutrons is not as efficient as when you use water, like light water reactors, the PWR, and the boiling water reactor, BWR, or in graphite, carbon-12 in that case. Sodium and potassium are not very good moderators. So the neutrons remain fast around, say, the kilo electron volt range. They're born at 2 million electron volt. And in thermal reactors, light water cooled reactors and heavy water cooled reactors, or graphite moderated reactors, we slow their energy all the way down to 0.025 electron volt in that case. Modern liquid metal fast breeder reactors have been designed to use sodium as a coolant. Sodium is highly interactive with the air and with water. In that case, if you have any contact between the coolant as water and the sodium, you get a fire. Same as lithium in lithium-ion batteries causing fires in existing electrical vehicles with lithium-ion batteries. So in that case, they use the eutectic. What is a eutectic? Eutectic is an alloy of any element, and the eutectic is the alloy of one or two elements in that case that has the lowest melting temperature. So in that case, whereas sodium at room temperature would be a solid, and you have to heat it to turn it into a liquid, you'll find that the sodium-potassium alloy that was unique to it is liquid at room temperature as a coolant. Notice that it's the same way as sodium or lithium. It is reactive with air. It can start a fire if it gets in contact with air. Initially, the experimental breeder reactor, from its name number 1, used traditional impeller pumps. Impeller means that they have basically a rotating kind of an impeller, or like the screw of a ship. And later, they were replaced by electromagnetic pumps, which is really the future for pumps for liquid metal reactors. How does a liquid, how does a electromagnetic or magnetohydrodynamics, to be exact, pump works. It works in an interesting way. If you have a magnetic field here, let's call it V, and you'll find that if you have a charged particle in the magnetic field, it rotates around the magnetic field lines. If it is positive with a certain radius, it moves in the other direction. If it is a negative, like for the electrons. So the interaction between a charged particle and a magnetic field goes according to what's called the Lorentz equation. You take the charge of the particle Q. If you have an electric field, it moves in the direction of the electric field. So if you have a condenser here, you'll find that an electron moves in the same direction as your electric field. But if you have a magnetic field, you'll find that it goes in the direction of the V cross V, V cross V. V is a directional vector, and V is a magnetic field. So in that case, if you don't have an electric field, V cross V now should be equal to mv squared over r, and simply the particle rotates around the magnetic field line. So use that to your advantage. In fact, in foundries for steel, you don't want to have an impeller made out of steel. It would melt in the molten steel. But an impeller that uses simply that V cross B product. So in that case, you get a magnetic field here perpendicular to the flow of the liquid metal. You find that you have basically a force on it, F, that makes it move. Actually, it will move perpendicular to this direction. And that's the basis of designing what they call electromagnetic guns. And if you watch the movie, The Hunt for Red October, anybody here? They had what they called the Caterpillar propulsion system that would be totally silent because it will not use any steam or rotating equipment. Simply that V cross B force would take the water and simply turn it into a jet. And in that case, the propulsion would be totally silent. So that's a theoretical idea. I think I had the officer in charge of the Naval ROTC write a term paper on it. Hopefully they may end up developing more ideas along this line. In any way, so it used also, so it has two very interesting aspects of EBR1. And in that first, it used the breeding. It used the eutectic of sodium and potassium as a coolant that is liquid at room temperature. You don't have to heat it like if you had sodium. And it used also those magnetohydrodynamic pumps in general. And here is a picture actually of that EBR1 plant in the desert of Idaho. And you could see it's a whole big desert there. On your way west, as I suggested, it's a museum now. It is not operational anymore, but it did prove for the first time ever that you can produce energy from nuclear processes. So the first thing, the first energy produced in the United States for nuclear energy was done here. They lighted up those light bulbs here. You see that string of light bulbs from the electricity produced from the EBR1 plant. The experimental breeder reactor number 1 at Idaho Falls in the desert of Idaho was followed later on by another reactor. In that case, they used sodium as a coolant. They didn't use the sodium-potassium eutectic, and they named it, aptly enough, of course, EBR2, experimental breeder reactor number 2. It was a fast reactor. It operated successfully for 20 years, but they retired it, and it supplied the city of Idaho Falls with nuclear electricity. I had the pleasure, it was very, very well designed, and I had the pleasure of walking on top of it while it was in operation. So that means that it was very, very well shielded. Nevertheless, that was the first reactor to produce nuclear energy in the United States. It was not in the world because the British had run a reactor before that thing, I think at Calder Hall. And in that case, the first nuclear energy was produced in the UK, not in the United States, but that was the second one. It has been declared as a National Historic Landmark in 1966, and of course, it is open for visits by the public. Well, the reactor was used as a way of exploring what happens when you have a transient or an increase in the power of a fast reactor. And let me quickly show you how that reactor looked like. This is actual picture of the EBR-2 core. It was a very long cylinder here with control rods in the core. So that's looking from the top. And it was very small. The reactor was here in that enclosure here. It was the size of a football, as a matter of fact. So this is the perspective of the core. You had fuel elements in the center, surrounded by what is called the blanket. That blanket contains rods that contain uranium-238. And in that case, the neutrons that are produced in the core interact with the uranium-238 in the blanket. And we get a chain of interesting reactions here. So you get a neutron to interact with uranium-238. Uranium, in that case, is 92. And that produces uranium-239. So it's still 92 number of electrons. Uranium-92, I want you to try to write down those equations because they are the secret of a nuclear age in terms of breeding. It is unstable. It emits a negative electron. It emits an anti-neutrino. And to balance the equation, it turns into the element 93. So the element 93 is what we call neptunium. It's named after Neptune, the Greek, basically god of the sea. And in that case, it's still neptunium-239. Neptunium-239 is, again, unstable. So that's 93 here. It emits, again, a negative electron. And it emits an anti-neutrino. Actually, there is a gamma photon emitted here too. Let me add it. And to balance the equation, you get here the element 94. What's the element 94? That is what we call plutonium. It's named after the planet Pluto. While people are debating whether it's a planet or an astral object, they keep debating here, the astronomer, and that's neptunium-239. So if you add those chain equations here, you'll find that neptunium-239 act as catalysts, uranium-239 and 239 act as catalysts. Why do we call them catalysts? From chemistry, a catalyst is a component that takes part in a reaction, but does not appear as an end product. So you get here the neutron interacting with that uranium-238, which is the most common isotope in nature of uranium. 99% of uranium is uranium-238, and then it turns into two negative electrons, two anti-neutrinos, two gamma photons, plus a new isotope, 94 plutonium-239. Because it is an odd numbered isotope, it can fission with any energy neutron. And the fascinating thing is that you would produce that initially, that neutron here by fissioning some uranium-235 to start the cycle, uranium-235 fission. But then after a while, as you produce the plutonium-238, you stop using that uranium-235 and you have that plutonium-239. And in that case, if you burn one atom of that uranium-235, you can produce one, maybe 1.25 maybe, or 2-3 atoms of plutonium-239. So this is the only process in nature that we know of where you can produce more energy than fissile material in that case than what you have used. I see that you may not have seen those reactions. So The competing process, just for completeness, if you haven't seen it before, is the isotope of thorium, thorium-232. Thorium-232 is the only isotope that happens in nature. The same process can be done with it. A neutron with thorium-232 turns it into thorium-233. I'll abbreviate it here a little bit. Thorium-233 decays into a negative electron, an antineutrino, and turn into not the neptunium now, but proto-actinium-233. It is not palladium, by the way. Pa is proto-actinium. Proto-actinium-233 turns into, releases a negative electron. I'll ignore the antineutrinos here and turns into the uranium-233 isotope, because that is thorium-90 here. That becomes 90, 90. This becomes 91, and the 91 turns into 92, which is uranium-233. If we cancel the on both sides the catalysts, a neutron here plus your thorium-232 basically produces for us 2 negative electrons, 2 antineutrinos, and you end up with the 92 uranium-233. And in that case, it's an odd numbered isotope, so it's fissile. It can fission with all energy neutrons. And in that case, we use all the thorium that we have in nature to turn it into uranium-233. Whereas in the existing cycle, we are only using the uranium-235. We are not using the plutonium-238. So our current cycle is extremely wasteful of the resources that nature is providing us with. So in that case, you could see that it had a core in the center surrounded by a blanket. This is typical of fast reactors, where the leaking neutrons are intercepted by uranium-238, producing uranium-239. The core would be here. Actually, they had an inner blanket, and the core would be right there in the center. And as I suggested to you, they imposed on it some kind of transients to study what is the behavior of fast neutrons so that they can learn how to build them. And they caused it intentionally to get into an accident. So the core there shown, as you could see here, this part in the center here, you could see that it burned, literally burned. It melted, and the core is no longer than a little ruler here, maybe 1 foot in length, almost the size of, well, a little bit more than a football. You could see the rods here. They had some spacers between the rods, and basically it was a core meltdown if we characterize it as an accident. So we had the core here in the center with the internal blanket rods, and then an outer blanket rods on the outside. And it was a successful reactor. It produced electricity, but it was very small in size. The core would be that part here with a steel cap on top. And it was destroyed and then replaced another time. This is more detailed replacement core configuration with a new core. Again, they wanted to learn about how to build fast reactors. And it was followed, as I suggested, with the EBR2 plant that operated for 20 years, producing electricity for the city of Idaho Falls. So the innovation was there. There are 3 innovations. In the first reactor ever built, they had 3 innovations: the use of the sodium-potassium alloy. They did the breeding, and of course, they used also the magneto-hydrodynamic pumps. And that should be the way that we use electromagnetic pumps in future reactors rather than using impeller pumps. So impeller pumps would be very hard to use in moving a liquid metal, or in fact, you can move it by the Lorentz force. The French call that equation, they don't call it the Lorentz equation, they call it the Joule equation. So it is here rewritten back again. And basically, if you don't have the electric field, the force now is the force for the magnetic field. And it is the same idea that is used in what they call a rail gun, or the magnetohydrodynamic gun, as a matter of fact. So they would have some kind of a little metal here inside a large gun barrel. The gun barrel is two parts, one metallic on top and the bottom here. It creates a magnetic field, and the force would accelerate the projectile at almost the speed of light. So this is an application for it. And this is an experiment that shows us that this magnetohydrodynamic force would work in water. Water from the faucet contains some salt, so it will conduct electricity. So what they did is here, they show us a small experiment, water that is ionized being propelled by an electromagnetic pump. So you would have a magnet on this side, and an electric field from the metal here. And you can see the experiment on the, basically some YouTube maybe experiment. You could see that the water or the liquid metal or mercury, any metal, would start flowing without having any moving parts, only the force from the magnetic field and just the force from the electromagnetic field when you have perpendicular electric and magnetic fields. And this would work with any liquid metal. It is used in foundries, in fact, when you want to move some liquid iron. That's what is used rather than impeller pumps that would melt in the iron. And you can use it for circulating lead. And the Russians had, in fact, one of the generations of their nuclear submarines that used lead as a coolant. Actually, a lead bismuth alloy. It would also move tin. It would move indium, any metal of your choice. So the first experiments then basically were intentional explosion of that EBR-1 reactor, but it proved that we can build those fast reactors. However, the further implementation of the idea of breeding was not adopted. Instead, the needs for nuclear propulsion for the nuclear navy in the United States and other countries brought in the light water reactor, where light water is a coolant rather than the sodium-potassium alloy. I told you that the Russians, in their what they call the alpha class of nuclear submarines, they did use a lead bismuth alloy as a coolant. And in that case, they had to keep that lead molten at all times. So they had to keep the core heated by steam 24/7. And of course, bismuth and lead are very corrosive. So at some point they had to abandon the whole idea, and they took the cores and dropped the cores of the reactors in the Barents Sea where they are still underwater today. Just water is a good shield for electricity. So the first accident that ever happened intentionally at that EBR-1 reactor. So let's look very quickly on how the accident happened, or how they proceeded in causing the accident intentionally. So to facilitate the design of the EBR-2, and it was followed, by the way, by another fast reactor in the United States. It was named the Fermi Fast Reactor. It was built around Detroit. And the Fermi Fast Reactor itself had its own accident where the core melted down and embedded itself in the concrete below the core. We'll study that accident maybe in more detail later on. So basically, they were testing whether they can increase the fuel to temperature of 500 degrees to see whether it would lose reactivity. Lose reactivity meaning that at a higher temperature, the resonances that absorb the neutrons in the resonance region of uranium-238 would widen up and absorb the neutrons. So what it means is that as the temperature increases, the absorption of neutron increases, and that would shut down the reactor. We call that a negative temperature coefficient of reactivity. Reactors in the United States, from the safety perspective, must all have a negative a temperature coefficient of reactivity, meaning that if the temperature increases, the absorption of neutrons increases because the resonances widen up, and that should shut down the reactor. It provides negative reactivity or a negative feedback effect. So they were testing whether it will lose that reactivity as predicted theoretically. The safety system that would automatically scram means shut down the reactor before it reached the test temperature, were also intentionally disconnected. So that was running an experiment, really. It was known that this could cause a meltdown if a scram of the reactor was not timed perfectly. But those reactions really in nuclear materials happen on the microsecond, not even the millisecond kind of time scale. So they were not able to shut it down in time. In November 29th, 1955, the plan was to scram the reactor when the power reached 1500 kilowatts. So it was a really low power, 1.5 megawatt of thermal power, when the doubling of the fission rate occurred at a 1 second interval. So that would be what's called the doubling time. When this moment arrived, an assistant misunderstood the operator's instruction and scrammed the reactor with a slow-moving control rod. So they did not insert the control rod fast enough. And as I said, the reactions, nuclear reactions with the nuclei occur on a microsecond level. Here, maybe they had hundreds of seconds or thousands of seconds. So he did not use the faster control rod. The operator quickly reached over and pushed the proper button, but the lapse had caused 2 seconds of time. 2 seconds caused an accident to happen. 15 minutes later, they had detectors all over the place. Detect radioactivity has been released. Why? Because the cladding around the fuel has melted. So the fission products in the fuel now were released to the environment, and half the football-sized core had melted. And the event produced no sound, no steam, no smoke, no explosions. It's just that the radioactivity was released. The scientists found in this event lessons to learn and saw an opportunity of perhaps making lemonade out of a lemon to learn how to handle a damaged core safely and efficiently in general. As a result of the accident, at the time, it was regulated by the Atomic Energy Commission headquarters. They decided not to tell people about the accident. They kept it secret. And so we learned from this that eventually you cannot keep those secrets. The news leaked 1 year later in 1956, covered the nuclear and national presses. The editor of a magazine at the time called Nucleonics warned the Atomic Energy Commission, AEC, that nuclear accidents were public business. He said, quote, apart from the bad effect that secrecy would have on attitudes toward nuclear safety, such withholding of news is wrong in principle. It is beyond the authority of the AEC to withhold information not affecting the national security. And because AEC operates in so much secrecy, public confidence in it will surely be undermined. And indeed, it was undermined in general. Analysis found that the influence of the high heat, the fuel elements had bowed and expanded. So basically the fuel element expanded, they touched each other, the coolant was obstructed, and it led to a positive feedback effect, creating more damage. The heat has been greater on one side of the elements than the other. And since the fuel was clamped at both ends, had it clamped on both ends, it simply bowed. It bent and touched each other. And in that case, a simple mechanical event in the future, it should be, if you build someday or design a fast reactor, you must make the ends be allowed to expand. If you keep them stuck together, they will bow, and as they bow, you stop the coolant flow, and the temperature would leak the system in general. The Argonne National Laboratory installed what would be named the ABR-1's last core. This one used plutonium fuel. So it was used really for experimentation, learning about different fuels and different breeding and so on. Experiments continued until Argonne National Laboratory, by the way, which is located primarily at the Fermi Lab in Chicago, also runs the Idaho National Engineering, well, it used to run the Idaho National Engineering Lab before it became an independent laboratory. They shut down the reactor in 1964 when they became ready to move with the EBR2 design, the successor of EBR1. And that was the next evolutionary step in the march towards commercial size fast breeders. Unfortunately, the fast breeder was not adopted by the United States. It was adopted by the French. So they built the Phoenix #1 and the Phoenix Super Phoenix #2 based on the same design as the EBR2 design. In the United States, the design was given to the Westinghouse company. So they tried to use the same technology as they use in light water reactors with lots of piping instead of cooling the whole core in a pool of sodium. The French did it right, like EBR2. The Americans were criticized by the engineering profession, and the reactor, the fast reactor that was named, in fact, Clinch River Reactor, it was to be cooled by water from the Clinch River around, in that case, Oak Ridge, Tennessee, was never built. The French have acquired experience on fast reactors, and indeed, in the Super Phoenix #2, the French also achieved breeding at 20% above 1.2% breeding ratio. The idea of breeding is the future of nuclear energy, the vision where scientists and engineers are interested in nuclear energy. It provides us with basically a practically unlimited supply of energy. Today, we are still burning that uranium-235 because it's very widely available, it's very cheap, and in that case, we haven't jumped yet into the breeding range. The first knowledge about it came into us from that famous EBR1 reactor. And that's the history of the EBR1 reactor in general. All right, so that was the experimental breeder reactor #1. I have to plan our time here. We want to study another accident that happened also in the Idaho Falls desert. And at the beginning, of course, nuclear energy was used by the military. The United States Navy, of course, built a reactor for naval propulsion. And the United States Army also thought, oh, let us also build a nuclear reactor. So the United States Army built what was called the Stationary Low Power Plant #1, and it was designated as SL1. And now that was also built, that's why I'm following it after the EBR1 accident in the desert of Idaho Falls. And it was meant to be a military reactor for remote locations. And it was a small power. So the SL here is small power. It was only 300 kilowatt electric. In that case, they used boiling water. So it was a boiling water reactor. And it was meant for geographically remote locations, like if they have radars, for instance, trying to intercept ICBMs coming from the side of Russia, they had to build them in the northern parts of Canada, a long way from civilization. Getting diesel fuel there to produce electricity would have been very expensive. So they started building those small reactors in general. Because it had to be at a remote location, it had to be small in size. They used highly enriched uranium. The enrichment in that case was 93%. So in that case, you get a very, very compact size reactor. And that level also would allow you to run a reactor for 10 to 15 years without having to refuel it. And in fact, that 90% enrichment is used in naval reactors. And land-based reactors are allowed only to build with an enrichment of 3 to 5% on an arbitrary basis, because the International Atomic Energy Agency allows countries to use up to 20% enrichment in uranium-235 in research reactors in general. It was accidentally destroyed in that case and reached what's called prompt criticality. It became supercritical. So it had a nuclear accident, as a matter of fact, in the same way as EBR1. So in that case, we had two criticality accidents happening in that case, and it was caused during maintenance. So notice here now that those two accidents happened before of human error. And you'll find that we identify in that case human error as the cause of either two of the accidents. And the human error will come back to haunt us later when we deal with the Chernobyl accident, with the 3 Mile Island accident, as well as the Fukushima accident. There are two other causes that are prominent in accident situations. Other than human error, you'll find that equipment failures take a role. And the third element is the design flaws. And we have to be cognizant of the three of them. This accident happened while they were performing maintenance on the control rods. And it was around the time of Christmas. So it was a very, very cold time in the desert of Idaho Falls there. And it happened where a crew was trying to perform maintenance on one of the control rods. It led to the deaths of 3 persons in January 1961. That was about 5 years or 6 years after the EBR-1, but in the same kind of location. So why did they build those small reactors, SL1 and SL2 and so on? It was meant for the distant or early warning system. And basically, these are dozens of manned radar systems around the Arctic Circle on watch against a possible attack from Russia with ICBMs. You want to detect them upon launch when they're being launched, because then you can intercept them. When they come back at you, they come down from space at several times the speed of sound. So you need interceptors that are hypersonic. You cannot do it. So your best bet is to intercept them upon launch rather than upon basically re-entry back. So the Army reactor was designated as stationary or portable or mobile, depending on the intended field application. And they rated them as low, that's L in the SL1 reactor, medium or high power. And they thought that they can build a 3 to 4 parts power plant that can fit into cargo planes, and then you take them to the location, even in Greenland, and assemble them together. And you generate a small amount of power. 1 megawatt thermal would be enough for a radar station in that case. It was hoped that ordinary air could be used as a gaseous coolant in the gas-cooled reactor experiment. Later, they replaced it with nitrogen as a coolant. And the mobile low-power reactor, it was designated not as SL1, but L1. So they investigated it too, but all these projects did not come to fruition and on a large scale. This is a picture of that SL1 reactor in the desert of Idaho Falls around winter, as you could see. It was a boiling water reactor with control rods. Usually in boiling water reactors, control rods come in from the bottom. In that case, they came in from the top. And basically, they had a crew that had to check one of the control rods. And as they were trying to pull the control rods had some kind of friction. One of the people pulling the control rods yanked the control rod out violently beyond the limit that you can move a control rod out of the core to make it super critical. So in that case, the system became super critical. The energy release was monumentally large. It boiled the water. The water formed a piston. The piston rose up. It threw the control rods up to the ceiling. The unfortunate thing is that one of the control rods impelled one of the workers into the ceiling, and the radiation level killed 2 other persons in the accident. So that was one of the first accidents that caused death in learning about nuclear reactors. And the interesting thing is that if you go to our describing the phenomenology of steam explosions, oh, that was a description of what happened in the SL1 reactors. So what were they doing? Look here at the diagram of the reactor. What they were doing is simply pulling the connections to the control rods at the top so that they can replace maybe some of the components of the control rod. The control rod was driven by a drive motor right there. So they had to take off everything on the top there and keep the coolant in the reactor core. And they started working on one of the connections here of the control rods that came in from the top. And this is the control rod mechanism. It was cruciform, meaning in the shape of a cross, like existing boiling water reactor. And unfortunately, it ended up with a human error. The control rod seemed to stick slightly, perhaps because other items in the reactor core had bowed, same as the EBR1, and invading the clearance spaces and placing pressure on the cheese. The 3 crew members entered the reactor at 9 p.m. They did it at night, 2 of them directly over or very close to the top of the reactor, working with a central control rod. At 9 p.m., something happened causing the reactor power to go prompt critical. So we have 2 accidents there where the criticality became prompt critical. Prompt means that the fission process happened with prompt neutrons, and we call prompt neutrons the neutrons that are generated from the fission process. Delayed neutrons are neutrons that are generated from the decay, the fission products, and in that case, I have a longer time, allow us to do some control. The prompt criticality can happen within microseconds, so the power increases in that case exponentially, really fast. In that case, when the power was released on a fast scale, a steam explosion that in fact we wrote the balance equations for in the previous chapter when we described the phenomenology of steam explosions. But the explosion was so serious that it basically threw out the whole top of the reactor. And here is a picture that was taken later on. It shows the destruction of the few of the damaged core of the SL1 core accident in that case. Both of them were accidents that were caused by human error. So in that case, we should take the human error as a major cause of many of the accidents in the history of nuclear power generation. As the system exploded, yes? That's a very interesting aspect of boiling water reactors, because in that case, the very high speed of heat generation totally boiled up the water. Now, what happens if you boil up all the water? You then have moderation of the neutrons. So the system shuts itself down. The steam explosion ended up shutting down itself, but still the energy was released in an explosive manner. It was not, initially it would have been nuclear, but it would have happened so fast that it became chemical. The steam really expansion turned it into a steam explosion rather than just a prompt critical or the fuel itself exploding. Why? Because you disperse the fuel and it becomes subcritical immediately. But the boiling water also, because it has boiled, you have no moderation, the system shuts itself down. All right, I think initially it's a prompt criticality. And, go back to the chapter on steam explosions, and you could see that what they call the borax experiments, as we have shown them, they initiated the steam explosion by withdrawing the control rods. So they create a supercriticality, and the supercriticality boils the water, and then it becomes a chemical explosion from the steam. Well, the steam now expanding, expanding, it creates a piston like in the model that we built about it. The steam went to the top, it destroyed all the top and all the components, as you could see it here in the barrel. The water is gone, so the fuel is sitting there without a reaction going on anymore. It cannot become critical anymore as long as you don't add water to it. Prompt criticality comes from neutrons that are born from the fission process when the system is moderating. But if you don't have a moderator, you get a spike and then no moderation anymore, the system shuts itself off. The loss of water of the coolant shut the system off. Yeah, and that's true. It was 93% enriched and makes it very compact. This is what the enrichment is in naval reactors. So it was a military reactor, remember, that was a military reactor. When it was moderated, it was prompt criticality. Once you evaporated the water and the evaporation process itself is a steam explosion. So it's a chemical reaction now. The prompt criticality did not act like a bomb. In a bomb, you need to keep the fuel compressed together. Once you dissociate it, it's not critical anymore. No. And that's what the Germans thought. Werner von Heisenberg thought that the bomb would be very large in size because we needed a moderator. The genius of Enrico Fermi is that he built a fast reactor. Remember the spheres of uranium-235 and plutonium-239 used in the Nagasaki and Hiroshima bombs didn't have a moderator. They were fast reactors, same as EBR-2 in a way. Okay, let me very quickly tell you the progression. The Navy continued, the United States Army continued trying to build small reactors. And one of them is a mobile low reactor number 1. You could see here they built it as different components. This is the pressure vessel there. And they built it in an atmosphere of ice. And it looks very much like a naval reactor. But it used nitrogen as a coolant, air, in fact, because air is 72% nitrogen. It was followed by a reactor they built very close to the White House, really. So ML1 concept was too advanced for basically the materials that they used at the time. They were not able to use the nitrogen as a coolant. It still remains as an alternate coolant for us as a gas if we don't have enough helium for reactors, and that should be some topic for a thesis research, that we can use air as a coolant. In the case of the low reactors, SL1 and ML1, basically the system leaked all over the place, and they give you detail about it. The important aspect of today's lecture, the 2 chapters here, is that in both cases, it was human errors that led to the accident. In the first one, the operator did not push the correct button to insert the correct control rod. And in the second case, it was the operator, if you read the detail, he yanked on the control rod, and instead of pulling it only a safe distance of maybe 6 or 8 inches, he pulled it 1 foot, and that system led to criticality. And these are human errors that contributed to those 2 accidents. And as we learn about the other accidents, we'll identify what were the causes of these accidents so that, of course, we can avoid them in future designs. And thank you for your attention. We went a little too far today just to answer the questions. I'll be happy to discuss the topic with you even more if you have time.